So now we're going to do a history of heat pumps. This is intended to be a sort of a soft entry into the topic, kind of fun. We're going to start 2,400 years ago. So this is a really amazing example of how to use evaporative cooling, which is the basis of the vapor compression cycle, how to use evaporative cooling to make ice. So this is a 2,400-year-old building. It's in Persia, now called Iran. And what they would do is on winter nights when it was starry out, and they could have the ability to just infinitely radiate heat from the water to the empty open universe. They would fill up this basin to different amounts of depth in order to take advantage of how cold it was that night. Want to make sure they'd made ice, and then they'd wake up really early in the morning, go out and harvest the ice and stick it into this super insulated building next door. This was done all over the world. Here's a great example of people harvesting ice in New Jersey in the early 1800s. And there wasn't another way of making ice until 1854. In Australia, there was an engineer who's trying to keep beer cold, and so he invented this machine in which he was using the vapor compression cycle to remove heat and make ice. That technology was evolved in the United States by Anheuser-Busch and other breweries who would make large amounts of ice and chill the beer and then send it off on rail cars with ice in the rail cars, insulated rail cars. Now, it's from here that we get that term a ton. A ton, if you're in the HVAC industry, refers to 12,000 BTUs per hour of chilling or heating work getting done. Well, back in the day, a ton of ice sitting at 32 degrees Fahrenheit and then melting into 32 degree Fahrenheit water over a 24-hour period, that did a certain amount of chilling work, and they would refer to that as a ton. But it's 12,000 BTUs an hour for 24 hours that melts that ton of ice completely into a 32-degree basin of water. So that scientific metric that they used at the time is still what we use today. That's its origin. In 1902, Willis Carrier, he's over in New York, he takes some of the technology that had been innovated by the breweries there to make ice, and he starts making an air conditioning unit. It's to chill a printing factory. They're taking pulpy hot paper and they're pressing the paper and then they're inking it and they're printing out newspapers. That whole process creates a lot of heat and humidity for the people who are working in there, and it also prevents the paper from drying quickly enough. So he invented a way of taking this chilling process and distributing it through the air and squeezing out the water. That takes off like a rocket. Everyone thinks it's a great idea. Chill the whole room. Don't make ice, make cold air. And it gets innovated in refrigerated rail cars that are sent all over the country. Here's an example of one. They also would serve out meat and dairy. Sometimes they'd take really important people in the refrigerated car, the air-conditioned car, but generally it was just for keeping food and drinks cold. That technology, Willis Carrier, who's a real leader in the United States, he goes forward with that. In 1933, he invents the first room air conditioner. This is something that could be in anyone's residence. Coming into the 1940s, you see it gets small enough that it can be put into a window. And there's a great release of happiness around the country when people are able to put in air conditioners in their homes. Now, in 1951, they start beefing up the room air conditioner into a whole house air conditioner and heat pump and do both those jobs. Here's a great illustration of the General Electric heat pump. You might recall from the Electrification 101 history that in 1953, just a couple years after this photo was taken, Ronald Reagan is hired by General Electric to spread the gospel of electrification nationwide, paired with really clean nuclear power. In this era, heat pumps start to grow all across the country in this new building type, the all-electric house.
The pride and joy of the man of the house is the Weather Control Center. A center that puts you in charge of the electric heating and air conditioning and the electronic air filtering of the entire house. If you like, the temperature of each room in the total electric home can be set individually. But the real heart of this home is clean, safe electric heating. A home is not totally electric without it. Yes, a new concept in living with the feel of the future is here today in this Westinghouse Total Electric Home. And the wonder of it is, total electric living is not expensive.
By the 1970s, they've gotten them fairly small. This is called a spam can. Over there on the left, that's a Carrier spam can. And then there's the 1980s version of that same heat pump, but a little bit larger because it's a 3-ton. The next really important innovation in the United States with heat pumps is in 2001. Mitsubishi brings over a fairly new technology they developed in Japan, which is integrating computers into the heat pump and making it so the AC electricity went through an inverter so that you could control the amount of electricity you gave to the pumps and the motor, and therefore you could control the speed of the process. So together with a computer that could read the temperature outside and the desired temperature inside and carefully control the amount of electricity that is going to the pump and the motor, they could then make it go faster when the temperatures got colder or slow down the process when the temperatures got warmer. And they're able to get a heat pump to go down to negative 30 degrees Fahrenheit and be able to be quiet the whole way. Having an inverter meant that the heat pump didn't turn on and then turn off and turn on and turn off. Instead, it just stayed on the whole time, either at a very low rate or at a very high rate. So starting in 2001, we have cold climate heat pumps that are nearly silent. That technology doesn't really pick up in the United States until about 2010. You start seeing them sold more widely into people's homes. And by 2015, the Propane Education Research Council was concerned enough about what they were seeing as market share loss in rural areas that they hired consultants to do a study, and they came up with this map. This map shows you where electric space heating is becoming predominant. It's the one that's gaining market share, and it's nationwide. And they explained in the report that the reason is because of advances in heat pumps being able to operate at colder temperatures. You can even see in California that starting in 2010 and going through 2015, in both rural and urban areas, what was growing in market share was all electric construction. What follows is an animation from This Old House, which will help you visualize how heat moves through a heat pump, both in heating and in cooling cycle.
There's refrigerant that runs between this indoor wall-mounted unit and an outdoor condenser. The refrigerant is very cold, so it absorbs heat that's in the room and transfers it outside, where it's released into the atmosphere. The refrigerant is recharged and is sent back into the building cold to capture more heat. But these units can also take the same process and work in reverse during the cooler months, capturing heat that's in the environment outside and transferring it to the inside to condition the space.
So here's a helpful animation that illustrates how heat moves through a heat pump.
The first thing we're going to look at is the air-to-air heat pump. These are the most common heat pump types. They often look very similar to a standard air conditioning split unit, with a unit located outside and another unit located inside. These can either work as a heating-only device. Alternatively, the more popular choice is to have a device which can provide both heating or cooling by making use of a reversing valve. We've covered reversing valves in our previous videos. Links to that can be found in the video description below. There are a few different ways to configure a reversing valve heat pump. I'll show you a simple, typical example. The main components we'll have in this type of system are the compressor, the reversing valve, the indoor heat exchanger, an expansion valve with a non-return valve bypass, a bidirectional filter dryer, a sight glass, another expansion valve with a non-return valve and bypass. Then we have the outdoor heat exchanger. We also have a controller and a number of temperature and pressure sensors around the system. In heating mode, the refrigerant leaves a compressor as a high pressure, high temperature vapor and passes to the reversing valve. The reversing valve is positioned in heating mode, so the refrigerant passes through this and heads to the indoor unit. Cool air is then blown over the indoor unit's heat exchanger to remove some of the thermal energy and provide heating to the room. As heat is removed, the refrigerant will condense into a liquid. Having given up some of its energy, the refrigerant leaves as a high pressure, slightly cooler liquid. The refrigerant then comes to the expansion valve and bypass. In this mode, the expansion valve is closed, so the liquid refrigerant passes through the non-return valve. It then passes through the filter dryer and sight glass and then passes to the second expansion valve. It will then pass through this expansion valve because the non-return valve on this side is preventing flow in that direction. As the refrigerant passes through the expansion valve, the refrigerant expands in volume and turns into a part liquid, part vapor mixture. This expansion in volume reduces the temperature and pressure. The refrigerant then heads to the outdoor heat exchanger. Here, a fan is blowing outside ambient air over the coil and adding heat to the cold refrigerant. The refrigerant boils at a very low temperature, and as it boils, it will carry away the thermal energy. As an example, we know that water will carry thermal energy away as steam when it boils, and we know that it boils at 100 degrees Celsius or 212 degrees Fahrenheit. Well, if we then look at some common heat pump refrigerants, R134A for example, has a boiling point of minus 26.3 degrees Celsius or minus 15.34 degrees Fahrenheit. Refrigerant R410A has a boiling point of minus 48.5 degrees Celsius or minus 55.3 degrees Fahrenheit. So it's very easy to extract thermal energy even at very low outdoor temperatures. We've covered how refrigerants work also in a previous video. Again, links to that can be found in the video description below. So the refrigerant picks up the thermal energy from the outside air and leaves the outdoor heat exchanger as a low pressure, low temperature, slightly superheated vapor, and then heads back to the reversing valve. The reversing valve then diverts this to the compressor to repeat the cycle. If the system is then switched into cooling mode, the system then acts like a normal split air conditioner. The compressor forces the high pressure, high temperature vapor refrigerant into the reversing valve. The reversing valve diverts this to the outdoor unit. The fan of the outdoor unit blows ambient air across the heat exchanger. This air will be a cooler temperature, so it carries the thermal energy of the refrigerant away. The refrigerant condenses as it loses its thermal energy. Having given up some of its energy, the refrigerant leaves as a high pressure, slightly cooler liquid. It then heads to the expansion valve, but this is closed, so the refrigerant passes through the non-return valve. It then passes through the sight glass and the bidirectional filter dryer. The next non-return valve is then closed, so the refrigerant passes through the expansion valve. As it passes through the expansion valve, the refrigerant changes to a part liquid, part vapor mixture, which causes it to drop in pressure and temperature. It then flows into the indoor heat exchanger. And in here, a fan blows the warm indoor air over the coil. This causes the heat to transfer from the air into the refrigerant, and so the refrigerant boils and takes this heat away. The refrigerant leaves the indoor unit as a low pressure, low temperature, slightly superheated state and flows into the reversing valve. The valve diverts this back to the compressor to repeat the cycle. Air-to-water heat pumps. These units work in a very similar manner to air-to-air heat pumps, but without the reversing valve. The high pressure, high temperature vapor refrigerant leaves the compressor, but this time it heads into a plate heat exchanger. On the other side of the plate heat exchanger, water is being cycled through a hot water storage tank. Cooled water enters the heat exchanger from the tank, and as it passes through the heat exchanger, it absorbs heat from the hot refrigerant. The water will then leave at a much hotter temperature and flow back to the hot water storage tank to repeat the cycle. As the refrigerant gives up its heat to the water, it will condense, and it will then leave the heat exchanger as a high pressure, lower temperature liquid. We've covered how heat exchangers work in our previous videos. Links to these can be found in the video description below. The refrigerant then passes through the filter dryer and the sight glass and then into the expansion valve. The expansion valve causes the refrigerant to become part liquid, part vapor state, and will be at a low temperature and pressure. It then passes through the outdoor heat exchanger, where the outdoor ambient air causes the refrigerant to boil. The refrigerant then leaves as a low pressure, low temperature, slightly superheated vapor and is then sucked back into the compressor to repeat the entire cycle again. The hot water tank then provides hot water to the radiators, sinks and showers within the building.